chemistry and measurements. It seems like there's two ways to really screw up with measurements. Here's one way, where you just didn't handle the math correctly. And another way of screwing up is, okay, you take good measurements and you take poor measurements. How do you manipulate and combine these different measurements that are good and bad? It all comes down to the rounding. How many digits do you carry in your calculations? And if you screw up with this, the results can be horrendous. You could send a missile to a wrong place. So let's take a look at this. Now, to help us out, we are going to write our numbers in scientific notation. In the scientific notation, we're going to be using powers of 10. And this little movie might give you a feel for what different powers of 10 actually mean. We are going to start with an image that is 10 million light years away from our own Milky Way galaxy. And notice that's 10 to the positive 23 meters away from Earth, from the surface of the Earth. So we're going to zoom in a factor of 10 every second. And we're going to zoom in as close as we can get to human knowledge. Every second, we're going to zoom in by a factor of 10. So right now we are at the border of human knowledge. We are at 10 to the negative 16 meters. And this is all theoretical. We think we're looking at quarks here. But the point is there's a big difference between 10 to the positive 23 and 10 to the negative 16. So just keep that in mind when you're writing your numbers in scientific notation. Now, this is a chemistry course, so let's start our discussion with matter. It doesn't matter what it is, all matter. All matter is divided up into two categories. Either it's a pure substance, or it's a mixture of pure substances. And how do you go between the two is physical processes. So you're not creating anything new. Either you're purifying it or you're mixing it up, making a mixture. So let's start with the pure substance category. If matter that we're talking about is a pure substance, it has to either be an element or a compound. An element, we recognize all 118 elements that are in our periodic table. Elements. Compounds, on the other hand, are just chemical combinations of our elements. So if you have a chemical combination of different elements, we can have compounds. They can be molecules, they can be crystals, but they're molecular combinations of our elements. Now, to go in between compounds and elements, we have chemical processes. We're actually changing what's going on, what's formed at the molecular level. At the microscopic level, we've changed things. The flip side, you're a mixture. You're a mixture of pure substances. Well, then it's either a homogeneous mixture or a heterogeneous mixture. Homogeneous mixture, another word for that is a solution. It looks the exact same throughout. A heterogeneous mixture does not look the same throughout. It has a different concentration in different regions of that mixture. So let's play around with this a little bit and see where we will fall on this above diagram with these different compounds or solutions. So we have some water, just pure water. That would be a what on this table? Water is H2O, so we're going to have a compound, right? That'd be a compound. What if you had salt? table salt. Table salt is a combination of sodium and chloride. So two things alone that will kill you, but together you can actually consume it. Okay, so this would also be a compound. What if we mix the two? Okay, I don't know if you can see it, but we've got salt crystals on the bottom. This is definitely a mixture, and it would be a heterogeneous mixture because the salt isn't dissolved. But once I get all the salt to dissolve, it becomes a homogeneous mixture. It's a solution. Here I have pure water and some dye. If I take the food coloring or the dye and just drip it in, right now I have definitely what type of mixture? It's going to be a heterogeneous mixture. It's definitely not the same throughout. But all I need to do is just stir it up. Now I have a solution, a homogeneous mixture. Let's see if we can determine whether the below processes are chemical or physical processes. Now remember, in chemical process, you're actually getting something new. In a physical process, nothing new is generated. It was always there. Okay? Here's ice. I just let it melt in my hand. I end up with a wet hand. But this would be a what process? Physical process, because I'm ending up with liquid water. I started out with solid water, same compound. Liquid water plus heat. So I can just allow it to evaporate using the heat from the room, or I could put a burner under here and heat it up and get it to boil. But either way, I'm starting out with liquid water, ending up with water vapor. Only the state changed. I didn't get any new compound, new material, so that would also be a physical change. How about steel wool and fire? So here's the fire. Steel wool. We're actually forming that steel wool is iron. It actually burns with the oxygen in the air to create iron oxide. It's crazy that metal burns, huh? So definitely a chemical change. Is distillation a chemical or a physical process? These refineries, like in this picture, they take oil and they get all this really expensive stuff out of it. They get jet fuels, they get gasoline, they get glues and all these other types of material all out of oil and a lot of things. So the point is how do they do it? They're going to place the oil and heat it up. And they're going to have valves and things, but the point is they're going to be collecting what they boil off. And they watch this temperature. And every time that temperature changes, a valve turns and they switch out and they collect something new. So how does this work? Whatever boils off the easiest is going to boil off first. And then once that's all gone, the boiling point goes up, change your valve, get a new container, and you'll collect something new. For example, let's say our oil only contained this red material and this blue material. Okay, so it's going to boil it, we're going to heat it up, and either the red or the blue material that has a lower boiling point is all going to boil off first, and they're going to collect it. And then once the boiling point changes, they're going to turn a valve and they're going to collect the red material. Here's an animation that might help explain it. So we heat it, and notice this is the condensation column. So we have the red and the blue vapors are boiling off, but notice there's a lot more blue than red. So the blue must have a much lower boiling point. It's very easy to boil off. So they're boiling off all the blue, and they're collecting all this blue material, right? So here's the boiling point of the blue. And watch this boiling point number 1. Once it changes, once all that blue is gone, right there, you see that? all that blue material boiled off, it's all collected. They turn the valve because the boiling point changed. So now they're just collecting the red material. So you're collecting pure components from the oil. There's a big money in this, and it works really, really well. So is distillation a chemical or a physical process? Distillation is definitely a physical process because all of these components were there in the first place. We're not creating anything new. We're just separating out the mixture. Okay, let's move on to significant figures. Let's say we want to measure the length of this toothpick. So we put it on this meter stick, and this is the 10 centimeter mark. And we just have to do our best because the lines are covered up. Right around, if that's 5, probably around 7 centimeters, maybe. So I'm just going to guess 7 centimeters. Okay, that's the ruler without lines. Now if I try the same thing on a ruler with lines, right about 6.5, 6.6, 6.7 centimeters. 6.7 centimeters. We didn't do a bad job guessing. Okay? That is the idea behind significant figures. You can use a tool that wasn't very good or a tool that's much better. And you can see that in the measurements, right? This is a much better measurement. There's more digits. There's more significant figures, okay? So let's play around with significant figures a little bit and see if we can recognize how many significant figures are in each of these measurements. 3.80. How many do you think? There's 3. That 0 is significant. Just go back. What if we would have said 7.0, right? Yeah, we would have been reading it to the 10th place, but someone read that to the 100th place, so it's definitely significant. 3.080. How many would you guess? There's 4. So try the rest of these. See how many. See if you agree with me. Did you write 1? There's 2. 1, 2, 3, 4, 5, 6. There's 6. Now, whether you agreed with me or not, there's a lot easier way to play this game to figure out the number of significant figures, and that's to always write measurements in scientific notation. Then all you do is just count the digits, and it's so much easier. So scientific notation is the way to go. What are the rules? Write any numbers so that the first part is, it's in this format, a times 10 to the n, and a is just a number between 1 and 10, and the n is an integer. And remember, an integer is just a positive or negative whole number. So let's try this. Let's first move the decimal place till we get a number between 1 and 10. There it is. 8.501 times 10 to what power? Well, we moved it 1, 2, 3 times to the 3. Now, is it a positive 3 or a negative 3? Remember that movie. Negative exponents are numbers less than 1. So we definitely have a number less than 1, so it should be negative 3. The number of significant figures, just count up all the digits. Count everything that's there, whether it's a 0 or not. 4. So write each of these in scientific notation, count up the digits, and see if you agree with what I'm going to write. 1, 2, 3, 4, 5, 6 times 10 to the 6. And I'm going to end up with 3.65. 0001. How many sig figs? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 1.0820. 1, 2, 3, 5. 1, 2, 3, 4, 5, 6. 3.825001020. Let's write down all the digits. Count them all up to get the sig figs. 2, 4, 6, 8, 10. The last one, 1, 2, 6.3060. 6 sig figs. Okay, significant figures and calculations. What if we had to take these two measurements and we had to manipulate them in the same mathematical equation, whether it was an average or what, it doesn't matter. The point is, how do you handle the rounding? There's one measurement isn't near as good as the other one. So it's interesting. To do this right, the rules are different whether you're adding and subtracting or multiplying and dividing. If you're adding and subtracting, you always report your answer to the worst resolution. For example, if you're adding and subtracting all these numbers, 1, 3.7, 29.8236, whatever. The point is, which one has the worst resolution? This one does. Report your answer to the ones place. So that's not so bad. With multiplication and division, report your answer to the smallest number of sig figs. So if we are multiplying and dividing all these, report your answer to only one sig fig, because that's the measurement with the least number of sig figs. And only do the rounding at the very end of these calculations. Otherwise, you're going to mess things up. Let's try it. Report each calculation to the correct number of significant figures. 1.53 plus 2.0. Well, you can do that in your head. That's 3.53. How many sig figs, though? So this measurement is to the hundredths place. This measurement is to the tenths place. Report your answer to the worst resolution. So we have to report our answer to the tenths place. So this works, but we should actually do some rounding here. 3.5. That's the best way to represent your answer. The next one. We're adding and subtracting. Which measurement has the worst resolution? Tenths place. Right? So report your answer to the tenths place. Do everything on the calculator. 1.581 minus 0.6701 plus 0.8. I get about 1.7109. But I have to report my answer to the tenths place. So 1.7. So go ahead and try these and see if you get the same answer as what I'm going to get. Here's my last digit. I'm just multiplying and dividing, so I better report my answer to only 2 sig figs. So 3.8 times 2.7, about 10.26. Report my answer to only 2 sig figs, though. So I can't write it as 10 because you're not clear whether that 0 is significant or not. You could write 10 point. That works. Or use scientific notation. 1.0 times 10 to the 1. Both of those would work. I'm going to do what's in parentheses first. 3.8 plus 2.72. I get about 6.52. And I'm going to underline that tenths place. Now I multiply 6.52 times 7.42 divided by 4.085. I get about 11.8429, a whole bunch of digits. Well, the bottom I've got 4 sig figs. Here I've got 3. Here I only have 2. So I better report my answer to only 2 sig figs. So that would be 12. Next one, 8.71 times 0.031 divided by 0.056. I get about 4.82167. Okay, here's my last digit. So which measurement has the lowest number of sig figs? So I need to report my answer to 2 sig figs. Ready right here. So 4.8. 0.71 and 81.8. Better report my answer to the tenths place. 0.71 plus 81.8, about 82.51. Report my answer to the tenths place. 82.5. Okay. Let's do the multiplication first. 934 times 0.00435, I get about 4.0629. Now you have to report my answer to only 3 sig figs. So 4.0629 plus 107, the whole thing, I get about 111.0629. I have to report my answer. Here's to the ones place. Here's the tens place. The worst resolution is definitely to the ones place. So 111. The last one. Here's the big test. Tenths place, hundredths place, sorry. 847.89 minus 847.73. I get about 0.16. Take that times 146.73. Okay. Now I have to report my answer to how many sig figs? The whole thing. Here I only have 2 sig figs. Here I have 1, 2, 3, 5 sig figs. So I better report my answer to only 2 sig figs. So I got 234.7.68. Report my answer to only 2 sig figs would be right here. So I have to write my answer in scientific notation to make this work. 2.3 times 10 to the 3. And we're going to be working with the metric system, so we should know these base units. For length, it's meters, symbol little m. For mass, it's kilogram, so we already have a prefix in there. Time is second, temperature Kelvin, and the amount of substance, a mole. So know these base units, be familiar with them. There's derived units, and those are just combinations of our base units. Area is just length times width. Square meters. Cubic meters for volume, length times width times height. And density, which we'll talk about briefly coming up here, just mass over unit volume. So kilograms over cubic meters. Volume also is used in the metric system with liters. So L is a liter. And some relationships are 1 cubic decimeter is the same as a liter. 1 cubic centimeter is the same as 1 milliliter. We have already referred to some metric prefixes, so let's jump into that. These are the only metric prefixes we really need to worry about right now. Little d is deci, c is centi, little m is milli, and k is kilo. So if we want to make numerical equivalencies between these prefixes and their base unit, where do you put the numbers? Well, 10 deci of anything is 1 of that thing. So 10 decigrams would be 1 gram. 10 deciliters would be 1 liter. Centi, you need 100 of them. So 100 centimeters would be 1 meter. 100 centigrams would be 1 gram. Milli is 1,000. So 1,000 milliliters is 1 liter. 1,000 milligrams is 1 gram. 1,000 milliseconds is 1 second. Kilo. 1 kilo is 1,000 of anything. So 1 kilogram is 1,000 grams. So let's just practice this a little bit. MS would be milliseconds, right? And there's 1,000 milliseconds in 1 second. So see if you can finish these up, and then we'll go over them quick here. Decigram. There's 10 decigrams in a gram. A kiloliter. In 1 kiloliter, there's 1,000 liters. A centimeter. 100 centimeters in 1 meter. So be familiar with these metric prefixes and how they relate to the base unit. Our last idea here is density. So here we have 2 cans of Coke, so they're exactly the same volume. And if I take the regular can of Coke and put it in water, it sinks. If I take the diet can of Coke and put it in water, it floats. So why? They have exactly the same volume. Well, they must have different mass. The Diet Coke is less dense than the regular Coke. Why? Because in the regular Coke, I've got that much sugar. Well, about roughly 40 grams of sugar. In the Diet Coke, I have about that much material of the NutraSweet or aspartame, artificial sweetener, about 10,000 times more sweet than sugar. So definitely the Diet Coke is much less dense. So know these metric prefixes and know how to convert from one to the other, and be familiar with these rules, right? When you're adding and subtracting versus multiplying and dividing, and make sure you do the rounding at the end to keep track of these significant figures. And lastly, when you're not sure, write a measurement in scientific notation. That'll then just count up the digits and you'll know how many significant figures are in that measurement.